Oh, is that where you got the background?
No.
All right. Good evening, everyone. Let's go ahead and get started. So we will continue our lecture on algorithms. Right. Last time we saw search algorithms, and then we saw one of the sorting algorithms. All right. So today we will look at the remaining sorting algorithms, and we'll finish the class off with all those. We'll look at four at least: bubble sort, selection sort, insertion sort, and then quick sort. Okay. All right. Do you guys remember bubble sort, or should I go over it again? A little bit. Huh? You remember? Okay. Okay. All right. So let's start with a clean slate of sorting algorithms. All right. So first up is bubble sort, and by the time we get to the end, you will see why it is called bubble sort. All right. So how does bubble sort work? Bubble sort compares two elements which are right next to each other, and then sees which one is greater and which one is smaller, and then swaps those numbers. Okay. For example, over here, this is an unsorted array. All right. Let's walk through and see how this is going to work. Let me make it slow. And we'll go ahead and pause it. All right. So first of all, the loop starts. Okay. Picks up the first. Oops. This one. Okay. It compares the first two numbers. All right. In this case, the numbers that are less should be at the beginning of the array. All right. Right now, it's in the correct position. 44 is greater than 3, so it's not going to do anything. It's going to skip to the next two. Okay. It's going to compare 44 and 38 now. All right. These two are not in the correct position. 38 is less than 44. So what it's going to do is going to swap those two numbers. All right. This is what happens. Okay. The next two that it is going to compare are going to be 44 and 5. All right. It's comparing two next to each other. So it's going to compare 4 and 5, 44 and 5. And since they are 5 is in the incorrect position, it's going to swap 44 and 5. Okay. So this is going to become this. All right. Now it's not going to worry about 38 and 5. It's going to skip to the next one. Now it's going to compare 44 and 47. Okay, so it goes to the next one. Compare these two. These two are in right position. Okay, so it jumps to 47 and 15. All right, these two are not. 15 is less than, so it's going to go ahead and swap those two numbers. Okay, next would be 47 and 36. Again, not in correct position. Swaps those two numbers. Goes to the next one, 47 and 26. Okay, same thing, comes over here. 47, 27, same thing, swaps those two numbers. So it's comparing right next to each other. Okay, it's just going down the line. Compare these two again, same thing over here. 47 to 4, 4 is less than 47, swaps those numbers. 19, okay, 47 and 50. 50 is greater than 47, so there's no need to swap those two numbers. So those two are going to remain in the same position. Okay. Last one, 50 and 48. There's the same thing, and swaps these two. Okay? Now, it's going to go back and start the same process again. All right? So it's going to go back, start the same process from the beginning. All right? It's going to do the same thing again. It's going to compare the first two again. Okay? These two looks fine. These two again. Compares these two. Compares these two. Okay? So it's basically comparing the two numbers, and it will keep doing this until the array is sorted. Okay, now the question would be, how does it know the array is sorted? And we will talk about that. So it keeps going, and it reaches the end, comes back, and starts over again. Okay, compare these two again. Okay, it's kind of slowly sorting, but still has a long ways to go. So looks like towards the end it's already sorted, but the algorithm of course doesn't know, so it will keep going on. Okay, it keeps doing this until it finds out that there is no swapping happening. Okay, it makes the whole round, it makes the whole flow, and if it reaches the end of the array and there is no swapping happening, that means that the array has been sorted. Okay, and what do I mean? How does it know? You would probably make a boolean flag and make sure that if the swapping is true, you keep sorting. As soon as it becomes false, this means that the sorting has happened, everything is sorted. Okay, so you keep going through this array over and over again until uh, there's nothing else to swap. So still swapping is going on, so it's going to continue doing this. Okay, keeps coming till here. No swapping has happened, but over here it happened. So this means my flag that I'm going to set, I still need to continue sorting this. Okay. Now, how do I know this is sorted? You need to have a flag like a boolean, which will tell you that you have gone through the whole array and there is nothing that has been swapped. This means the whole array has been sorted. Okay, so we could keep doing this still. Okay, still happening. Okay, so if you notice towards the end, all the numbers that are larger are coming towards the end. That's why it's called bubble sort. It bubbles the larger number towards the end of the array. So it's like bubbling these numbers, and it's kind of making moving them towards the end of the array. Okay, that's why it's called bubble sort. Keeps going. Still a one swap. Okay, compare these two. Okay, in this iteration, it did do a swap, so it will keep continuous sorting. But in the next one, there's no swap that should happen, and that should be the flag that you will be like, okay, I have not swapped in this whole iteration, so this means my whole array has been sorted now. Okay, that will be the endpoint of this algorithm. Okay, again, how does this work? It starts with the unsorted array and then compares two numbers which are next to each other. All right, starts with this one, compares the first two, okay, and then keeps going the same way. All right, so adjacent numbers or indexes are being compared, and if the one that is next to the previous one is greater, is going to swap those two numbers. If they are not, then it's going to keep it in the same position. All right, this is how bubble sort works. All right, any questions? No questions? Everybody understand? All right, who's going to whiteboard this? Have to do it. We're going to do all whiteboarding today. Once you try. It's not difficult. I'm telling you, it's easy. There you go, Chris. All right. Initial ones are easy. As we move towards the next one, they're going to become a little bit more difficult, but it's not still. And if you're not whiteboarding, I would highly recommend start writing on a paper pencil. See if you can come up with the algorithm for this one.
Should I write it as a function?
All right. Let me do this. So you have a function, yeah, and I'm going to give you one function called swap, and in this function you can pass in the indexes I1 and I2, And you can assume what this function is going to do is going to swap these two numbers and return you. So you don't have to worry about the swapping part. You can just call this function, right? And you can be assured that those two numbers are going to be swapped. Right? For example, what I'm saying is you will have a condition where you need to swap those two numbers. So just call that function and assume that the swapping is done. So yeah, create a function called bubble sort, and within that you can go ahead and start the algorithm. Okay, let's suppose you're getting an array. Yeah, you're getting an array in the input. Okay, yeah, that's good. All right, so you have an array of unsorted integers.
I don't quite remember the syntax.
Okay, go ahead. We'll help you. What are you trying to do?
Sorted equals false.
Okay.
Do stuff.
So while, and then you can write parentheses, and
Oh, that's specific.
yeah, here's the. So while,
Sort of like that.
okay.
Yeah. Or
Okay. Okay.
okay. For check everyone if I is greater than I plus 1.
Okay. So it'll be the index, right? So you're saying array index I is greater than I plus 1. Okay.
And do the swap. That's a 1.
Okay. Yeah. Okay. So those two numbers have been swapped. Okay. What happens next?
That sorted still equals false.
Sorted is still false. Okay. So this is the condition. Let's suppose you are on this one. Okay, so I'm comparing, let's start with this one, 47 and 15. And then it says, okay, those need to be swapped. It swaps those two numbers. Okay, and sort is still false and keeps going. Okay, and then does it, the for loop ends. Yeah, okay.
End of the for loop.
So end of this for loop, do you know this for loop starts from here and ends?
Yeah.
Okay. What happens? It has to come back again.
It should be the for loop ends, and then it's sorted. Still false.
Okay. So it goes back to the while and then starts again. Okay, and then starts again, and it keeps running forever. Right? That's close. Okay.
Does it work if you do it like a while loop?
Yeah, I would. I don't think it works. It's going to work with a while. Or maybe let's see. Um, so why don't you move the sorted boolean? When does sort becomes false? When something swaps, right? If there's no swap, then would it be false or true? Uh-huh. Right? So if I is greater than 0, it will go ahead and swap it, right? So this means sorted should be false over here. So this is okay. Okay.
Okay.
Um, no, that's one thing. Yeah, you have to put false over there. Yeah. So you are saying every time the swap happens,
Yeah,
it's not
first
sorted.
swap, obviously false.
Okay. Now, how do I set it to true? How would I know if it's true?
For those two.
So there's no place.
Yeah.
So there's no place for us to set um, sorted is equal to true. There's no good place in this algorithm, right? If I set it somewhere, then my while loop is not going to run because you are saying your while loop only runs when sorted is false. Okay, that's it. What would you do in that function?
If sorted is false,
If sorted is false.
you have to have sorted out.
Okay, how about you remove the while and put another for loop? It's doing the same thing. What if try to think in terms of two for loops? So why do I need two for loops? One for loop is going to keep running this over and how many times is it going to run? It's going to run these many times. If these are, what are these? Huh? Right? Potentially every time. So there's a loop that has to run every single time. Once this is over, then it comes back over here, runs again. Then comes back over here and runs again. And then there's an inner loop, a nested for loop, that is running for just one time. Okay. So what I mean is over here. Yes, and then there should be an outer loop instead of while that should run for from 0 to whatever the length of this array is. Right? How many times the outer one should run? It is going to run n number of times, the same number of the length of the array, right? So you will already have a breaking condition. You don't have to have a sorted while because that for loop outer one is going to run for limited number of times. How many number of times? These number of times, whatever the length of this array is. And that's what we require. So instead of while, we can just create an outer loop that runs for the same number of times. Mm-hmm. Okay. Okay. So it runs. All right. So we need to declare our sorted variable somewhere, right? So let's do that. So where would you put your sorted? Okay. And what are you going to assign to it? Okay. So my initial value for sorted is false. This means I'm assuming that it's not sorted. All right. So it goes inside, loops through this, goes ahead and still keeps sorted as false, which is correct. Okay. Now, how do I set it to true? At some point, I need, this is going to work. This is correct. If you remove the Boolean variable, sorted, this algorithm is bubble sort. But what is the problem with that? The problem is going to run, even though if the array is sorted, it's going to keep running that array over and over again, even if it is sorted. Okay? So, what I want to say is, let's remove these for now. Yes. If you no. So you have to have an if condition. So if you come up with this is your first try at coming up with this algorithm, and this is correct. It's inefficient. It's extra inefficient, and the reason is it is going to keep running for the whole time, if you look at the loops, even if the whole array is sorted, right? It's going to keep running. The only reason it's going to stop is once this condition becomes false, right? When it completes this iteration, then it will come back and say, okay, it's done. But this is going to work. Okay. The next question would be, how can you make it a little bit more efficient? More efficiency is if I have gone through the whole array and there are no swaps, then it means everything is sorted. I don't need to run my for loop. I can say break the condition and stop looping through again. So how would you solve that? So you had the condition, I removed it. So when the swap happens, you need to do sorted false. So that will come back again. So if you are swapping, this means it's definitely not sorted. Okay? All right?
No,
So you need a, okay.
maybe if you could do it. No,
No, not over here.
after this one.
Yeah.
Not like this way.
Okay.
And
What would be your starting condition for sorted? So if the swap happens, you're saying sorted is false. Okay.
we fully fall,
Uh-huh.
and we would just have this and this.
The whole thing in an if? You're close, a little bit.
That's this one. No, because we still run this one every time.
Yes. So how about this? Move your sorted, where you have sorted as false. Move it inside the outer loop. Okay, move it inside the outer loop and set it to true. Do that and see what is happening. So inside my outer loop, where I have j equal to 0, the next line would be sorted is true. What does this mean? What do you think this is
So
doing?
you're assuming it's true. But
It's true.
This
Yes.
happens when you code.
Yes. If you do this, then it goes ahead and do this one. If it never comes under the if condition, what would be the value of sorted? It's going to be true. Right?
You s-
And then towards the end,
Yeah, you still need this.
yeah, no, you don't need this. You need an if condition over here. So, well, so now this loop runs, there's no sort. Right? Let's suppose everything is sorted. Sorted is true, but you need to stop this loop from running anymore. So over here, you need an if condition where you are going to say if it is sorted, then break. Like don't run this loop. Remember, this outer loop is still going to run, right? It's going to keep running. Over here, we have determined that everything has been sorted. So I need to stop the outer loop as well. How do I stop the outer loop now? At the bottom, I need a if condition, which is checking if everything is sorted. Basically, if sorted is true, then what do? I do just break. Uh-huh. So your if condition, and then put a curly braces at the end so that we know it is for the outer one. It's for the outer loop. Yeah. And then the function. Okay. So go over it one more time. So our for loop starts the outer one. It says the assumption is my array is sorted. Okay, I'm saying the sorted is true. Okay. Now, if a swap happens, it's going to set it to false. This means it's false. It has happened. The swap has happened. I still have some elements in my array that need to be sorted. So it comes over here, checks this condition, says false. Okay, I need to go to the next one. Okay, I need to go through the next flow. I need to go through a next iteration. You get it? Okay. So why do I need two for loops? Again, it's because I have to loop through within. This is the inside one, and then it has to keep doing it until everything has been sorted. Okay. Well, thank you. At least. Okay. Now we talked about big O, the time complexity of this algorithm. So what do you think is the time complexity of this algorithm? Remember, we have the choices are these. If I had to ask you what is the time complexity of this algorithm, what do you think is the time complexity of this algorithm? Chris, do you know what is the time complexity? N squared. Again, why? Because I have two nested loops. So this is going to run n times, and this is going to run n times. So if we have a nested loop, multiply these two, is going to become n squared. That's the red one. Yes. Okay, highly inefficient algorithm. All right. Remember what I posted this chart as well. So bubble sort is somewhere over here. Okay. In worst case, it's pretty bad. Um, Average case also, which means that the array is partially sorted, still n squared, and the reason it will keep going through the whole thing over and over again. Best case, if there are only like few items that need to be sorted, then bubble sort is good for that. Okay. All right. So let's look at the next one, the selection sort, and we covered selection sort a little bit. Selection sort is so it selects the first number and then uh, makes the assumption that that number is the smallest number in the whole array. Okay? It selects the first number and says that this is the smallest number in the whole array. Okay, let's pause this. Okay, for example, over here, it starts with the first element of the array, says 3, and makes the assumption that 3 is the smallest number in this whole array. Okay, what does it do after that? It compares this number with every single item in the array and tries to see if there is something that is smaller than 3. Okay, if it is, it's going to say, okay, this is the smallest number now. For example, in this case, it's going to start from the beginning 3. Look at 44, nope, 38, still larger, 5, larger, 47, larger, keep going until it reaches 2. And it sees that 2 is smaller than 3. So then it is going to say the smallest number is 2 now. Okay? You will see it hasn't done any swaps or anything. It is just keeping track and saying this new number that I found that is smaller than my current number. I'm going to assume this is the smallest one. And the reason is there is still some part of the array that is left, which it has not compared. Okay, so there might be a number that is smaller than 2. It has no idea. Okay, so it makes a point, it makes it, notes it, but it doesn't swap anything. Okay, it keeps continuing until the end of the array. So it checks for any number that is smaller than 2, reaches the end of the array, it is not. What does it do? It swaps this index with this one. Okay, and the reason is because there is a smaller number. Okay, and that smaller number should be at the beginning of the array. Right? What happens after that? It starts with the next one, 44. Okay, same assumption. It says 44 is the smallest number in the remaining part of the array. Okay, and then it's going to compare that number with each one of them until it finds a number that is smaller than 44. For example, 38. Smaller? Yes. So now the assumption is now 38 is the smallest number. Okay? And then it starts the process again. Looks at the next one, 5. 5 is smaller than 38. So my new minimum is 5 now. Okay? Again, please note in selection sort it hasn't swapped it yet. Until it reaches the end of the array, it is not going to swap any numbers or anything. Okay? It's just making a note. Basically, you have a variable you're assigning, you're updating it to a new minimum. Okay? 47, same 5, keeps going until it reaches 3 again, right? So 3 is less than 5, so 3 is going to be the new smallest number in the whole array. All right? But again, we still have 5 more elements to check, so it checks reaches the end of the array. These are the 3 is the smallest number in the remaining array. So it's going to go ahead and swap this with the second one. Okay, again, the reason it swaps with the second one is because it knows everything before that has already been sorted. There is no possibility that a number could be bigger than 3, which will come before. Okay, starts with 38 now. Same assumption, smallest number, find 5. Now 5 is the smallest number. Keeps going until it reaches 4. Now 4 is the smallest number. End of the array. What happens? Swaps the this number with the index number 2. Alright? Goes back over here, starts with 5, tries to go C. Okay? Didn't find anything, remains over here. Alright? 47, 15. Anything smaller than 15? No. So it's going to go ahead and finish this and then swap these two numbers. Again, 47, 36 smaller, yes. So this is the new minimum. 26 smaller, yes. This is the new minimum. 27, this is good. Fine. 19, yes. This is going to be the smallest number. End of the array. It found that 19 is the smallest number. It's going to swap these two numbers. Okay. Same thing. 26 is the smallest, and it's going to swap these two. Okay. 36, 27. 27 should be the smallest one. Swaps it again. 36 should be the smallest number. But also note that it has no idea until it reaches the end of the array. So it will keep comparing even though we can tell that there's no number smaller than 36. It's still going to compare because it has no idea if there's a number smaller than that or not. Okay? Reaches end, nothing, stays over here. Goes to 44. 38 is the smallest, and then comes over here. Okay? Comes here, 44 is the smallest. That should be the smallest, so 44, 46. Okay? 46 is in the right position, but it has no idea, so it's going to still go ahead and compare and try to find something. Doesn't find, stays over here. 47 looks like in the correct position, remain. And then, okay, reaches the end of the array, and everything should be sorted. Okay, so this is selection sort. It selects a number, makes an assumption that this is the smallest number, and then compares that number with the remaining with the whole array, right? With all the indexes that are after that number. Compares with them, finds a new minimum, and then swaps those two numbers. Okay? Again, it does not swap. The bubble sort is swapping as it is going through. This only swaps when you reach at the end of the array, and then it goes ahead and swaps those two numbers. Okay? Alright, who wants to do this one? Again, it should be okay. This is still, okay, here's a hint, you still need nested loops.
This one's not in square.
It is what?
It's not in square. It's less than square.
Again, so the reason I was saying is, the reason you are saying it is not n squared is because the outer loop is going to run, let's suppose, 10 times, the inner loop is going to run 5 times. Like less number of times. Yeah, but you always approximate when you're considering the words, the case you're considering like million numbers. So in a length of million array, 5, 10, 15, 100 doesn't really matter. So that's why they kind of approximate it. It should be like n into n minus 1, but we approximate it and say n squared. Yeah, it doesn't really Um, few numbers here and there wouldn't make a difference. What is it? Do you use it in your real life? No, nobody is going to ask you to write this in your real life. But this is the basis of if you understand this, you can solve a lot of algorithms using the same concept over here. Okay? Yes, of course, nobody is going to say, write me as selection sort. Okay? But you are going to get a question that is kind of based on this. Okay? The same concept. If you're comparing these two and swapping it, binary search, you have two pointers. Those things you will see if you practice a little more lead code, you will see those kind of will be used. Okay? So, selection sort. So, I'll write so you will have a selection sort function. Let's suppose you're getting an array here. Okay? So, who wants to take a stab at this one? Josh? I know you were requesting whiteboard and you want to give it a try.
I'm not very confident.
Give it a try. We'll help you. Okay. So best way is talk about it, and there's the marker. Blue. Try the blue one. So what are you thinking for this one?
I think it's going to be, well, I know it's going to be a nested for loop.
Okay, I'll give you it. It is going to be a nested for loop. Let's start with that. So the first thing would be why do we need a nested for loops? What is the outer one doing and what is the inner loop doing?
The other one is going through the entirety of the array.
Exactly. Okay. Yeah. So let's go ahead and write that one out. That's a simple one. Okay. Yeah. And then you will say I is um, less than the length of the array. So it would be arr dot length. Okay. And then I plus plus. Right. So you're looping through the outer array. Okay. All right. What's the next step? So what does the algorithm do? It picks an element and assume that that is going to be the smallest one, right? So how do we translate that into code? How do you pick the first element and go with the assumption that it's going to be the minimum? It has the minimum number. Okay, yeah, that's a good start.
I couldn't just do I as 0. Because then it's just going to assume.
Yeah, you cannot do I is equal to 0. You're right. Because and the next iteration is going to change. So what is, yeah, but you're trying to find the element inside the array. So this is going to assign the index. Okay, let's go with it. Okay, let's say you have picked up the index and this is the minimum index. That's okay. Okay, now the next step is you're going to loop through again and compare the minimum that you have picked to all of these. So you need another for loop, right? Okay, now what would be the starting point for this for loop?
Yeah, I plus 1.
Okay, why I plus 1?
It wouldn't be looking at I. It would assume this is the minimum.
Uh-huh.
It'd look at I, then it'd go to the next one.
Next one, excellent. Yeah, so it's going to be I plus 1, yes. So we're going to start with I plus 1 and go to the end of the array. Yeah, I is greater than, let's say, arr dot length.
J plus plus.
Yeah, J plus plus. Okay. All right. So now what happens inside this for loop? So now I have two numbers and I'm comparing them.
Hmm.
And if they are, if the one is less than that, it sets the new minimum.
Okay, so if
Uh-huh.
if J greater than
Okay. What did he say? If J is greater than?
I,
Looks like a less than. Is it less than?
oh, I don't think two.
No, it's any one of them would do, but the condition, the logic changes.
Okay, I always get the two mixed up. I'm terrible.
So you're trying to greater than it's the opposite way. Okay. Okay, so J is greater than I. Okay, so what happens in this case? So this is a condition if you look at the screen, Josh, over here.
I think I had it right the first time.
Yeah, you were trying to do less than? Okay.
Less than. Like I said, I only get the two mixed up.
Okay. So if J is less than I, yeah, that looks better.
Then
Yeah. Yeah, that's correct. So that's my new minimum.
Hmm.
Okay, and that's the end of my if condition. Okay, that's good. Yeah. So now I have a new minimum, and it keeps going through the whole loop until it reaches the end. Okay, reach the end. Now I have to do the swap. So, for example, in this case, I found 2.
Mhm.
This is the new minimum, and that's your if condition. All right.
Okay.
This is my new minimum, so it says red. Keeps going to the end. At the end of the array, my starting minimum was a little bit different, and my ending minimum is different. So this means I need to solve those two.
Mhm.
Okay. So I need one more if condition, and then you can call the swap method that I have. What would be that condition?
Can I phone a friend?
Okay, yeah, no. I mean, people can help. So we are missing one if condition. So this has happened, this algorithm is correct, it has reached at this point. Okay? Now what do I need to do? How do I swap these two numbers? So you can use my swap method, so that's not the problem. But I need a condition. And the condition is only if my starting, this one, is smaller than my new minimum, then I need to swap these two, right? So how do I translate that condition into code? What is my starting minimum? What variable? Huh? Any idea? Anybody? One more condition.
Amira and got this. What's next in the condition?
Array index I.
If what? Chris, what is it?
Array index I is greater than the minimum.
Oh, there we go.
You don't change. Well, okay. If the minimum is less than array index I, then you swap.
Yeah, write the condition what he's saying. If I is what? Less than or greater than?
If it's
Yeah, close.
array I is less than the
Okay.
minimum.
Okay, if I is less than minimum. I less than minimum. Okay. And then you can call my swap and this write swap inside it. It doesn't matter. Okay. So is this condition? What do you think, Chris? Does less than or greater than actually matter over there? So I is my minimum, starting minimum, okay? And my algorithm already has determined that there's another minimum. It already knows it is less than. How about not equal to? So if the minimum, my starting minimum was this, right? And I found a new minimum, right? If they both are different, I just need to swap them. It doesn't matter if it is greater than or less than because it has already determined the minimum, so it is always going to be less than that. So the condition would be if I is not equal to minimum. Change the less than to not equal to. Not equal to min. Okay, then go ahead and swap. So what am I doing? My I is right now index 0, right? Set it to minimum. It overrode over here, right? It got overwritten by a new minimum, all right? But my I is still 0. So I'm saying if this one, my starting minimum is now different. If I found a different one, I need to go ahead and swap these two. So I'm going to go ahead and swap these two numbers. Okay? And then it keeps going, yeah.
Should be good.
Yeah, should be good. All right, well, thank you, Josh.
But what if you had two of the same?
Huh?
What if you had two indexes with the same number?
It will go ahead and swap it. Well, if they both are same,
I guess it would just skip it and then eventually.
yeah, eventually they will come back. Yeah, that's why it's not a efficient one and cannot tell if it is equal. Eventually it will be sorted for sure, but yeah, it's going to swap those two numbers and go on to the next one. Okay, what is the time complexity for this one? N squared, 2 for loops, both are running, has to be n squared. Okay, so selection sort also is remember n squared, and in all cases, in best, average, and worst. Now best case means, let's suppose the whole array is already sorted. Okay, understand that even if the whole array is sorted, this algorithm is going to will have no idea the whole array is sorted. It's going to keep ahead and loop through the whole array over and over again until it reaches the end of the array. So that's why even as in its best case, it's still n squared, which is still a pretty inefficient algorithm. Okay. All right. Let's look at the next one, insertion sort. Okay. So insertion sort is, when we go through this one, you will see it kind of looks similar. Okay. Instead of selecting, it's going to insert the minimum. Okay. What does this mean? Let's look at the insertion sort. Let's pause this. Okay. Let me go to a few elements so that you guys can actually see the difference. Okay. So same thing, a loop starts off, right? We'll come back to the initial ones. Okay. Let's suppose you are at index where 38, it has selected 38. Okay. So what is it going to do? It is going to compare 38 to every single element that is behind 38. Basically, these ones. Okay. Insertion sort kind of picks an element and goes back. Alright? So for example, over here it selected 38, and then it's going to compare 38 to 44 and then 33 and try to insert it in the correct position. Right? What do I mean by this? For example, starts with 38, compares with 44. Okay? 38 should be over here. Alright? But notice, why is the visualization a little bit different? It moves the index, the value over here, to the next one, but it does not assign this one to this index. Okay, that's why there's a gap right now. All right, it's going to compare it to 3, small, so this is the right position, and it's going to insert that. All right, let's look at a few iterations to clearly understand that, and then I'm going to start from the beginning. It's kind of hard to see if you have like less numbers. Yeah. Let's start with 5. All right. So what does it do? It compares 5 with every single element that is behind, that is less than, that is behind in the array. All right, that has already been gone. Okay, so it kind of moves backward. It picks a number and moves backward. So it's going to compare with 44. 5 is less than 44. Okay, so it's going to move 44 to the next one. Okay, it is moving the array ahead. Now it's going to compare 5 with 38. Still small, so it's going to move 38 over here. Okay, now it's going to compare its 5 to 3. All right, 5 is greater than 3. This means this is a position that it needs to stop. There is no number that is going to be less than 5 anymore. Okay, and then it's going to go ahead and insert itself over here in this open position. All right, let's look at the next one. Starts with 47. It's going to compare every single element in the previous array, in the previous indexes. So it's going to compare with 47, 38, 5, and 3. Compares with 44. All right, 44 is less than 47. Does it need to go back and compare the rest of them, or this should be good? Is there a possibility that there's a number that is smaller than 44 in the previous part of the array? Is that a possibility or not? Yeah, there's no possibility. All right, so if it finds the number that is already smaller to it, that's the position it's going to stop. Right, so it says 44 stops over here. The reason is there's no possibility that there's a number that is going to be smaller than this. It has already sorted it out. Okay, let's try 15. Compares with 47, smaller. Okay, goes ahead and moves it. 44, yes, goes ahead and moves it. 38, yes, goes ahead and moves it. Compares with 5, so the number that it is comparing is smaller. All right, so every number before that is going to be smaller. There's no possibility that there's going to be a number that is smaller than 15 anymore. So it's going to go ahead and stop. So the condition is if my current, for example, 15 over here, is greater than the number that it is processing, keep doing it. As soon as you find a smaller one, stop it, and that's the position you need to go ahead and insert it. Okay, let's look at 36. 36 compares with 47, keeps going until 38. Okay, still compares 36, all good. 15, it says, okay, so the number that I have found is less than 36, less than what is my current position. This means this is my stopping point, and I'm going to go ahead and insert myself in that open position. Okay, goes on to the next one. 26 does the same thing, keeps moving as long as the number is greater than whatever number it is over here. Okay, it's going to go ahead and keep moving. So this insertion sort compares all the elements in the previous array, goes kind of behind. Okay, so if you have a for loop, you are remember our for loops are for I equal to 0 to length of the array, then it goes to 0, 1, 2, 3. In this case, the for loop is going backwards. Start with a maximum number, kind of goes backward. All right, keep that in mind. Okay, so it has to go behind. 26 compares with 15. This is the stopping point. Stops over here. 27 keeps going until it finds a number that is smaller than 27. Smaller, yes, and that's the stopping point is going to insert itself. 2. Okay, so you are going to keep processing until you find a number that is smaller than 2, or you have reached index number 0. Or the array, there's nothing else, you have reached basically -1, or you have processed index number 0, and there's no other place to go. This means the number is probably the smallest number in the whole array. So that's why 2 comes over here and stops. So 2 conditions. Keep processing until you find a smaller number, or you have reached basically the starting of the array and there's nothing else to be processing. This means this is the place where you're going to put your sorted number. 46, just 1, moves it over here. 44 is less than, so this is my stopping point, stops over here. 4 is going to go back all the way until 5, and then it's going to compare itself with 3. Smaller number, that's the stopping point. Okay, 19 keeps going until it reaches 15. Since 15 is smaller than 19, that's the stopping point, and it's going to insert itself over here. Okay, 50 compares with 47. It has already found a smaller number. So this is the stopping point for 50, right? It can't go behind. It can't go back because there's no possibility that there's a smaller number than 50. Okay, so keeps it over here. 48, okay, finds 47, smaller number, so this is the correct position, and it stops over here. Okay, goes to, since it has reached the end of the array, that would be the stopping condition, and it comes out of the array. All right, any questions? So similar two loops, the outer loop, why? Because it has to go through the whole thing, and an inner loop, but this time is going backwards. Okay, the inner loop is not going forward, it's going backward. Okay, for example, if you start in the middle, let's go back. Okay, if we are on 19, the inner loop has to go back instead of going forward. Just like our bubble sort and selection sort, our nested loop, the inside loop was going forward, right? It was starting from 0 or I plus 1 and keeps going forward. In this case, the inside loop is going to go backwards, going to compare this one. That's the main difference between insertion sort and bubble and selection sort. Okay, two loops, the second is going backward, and the condition that it is going to stop is the number that it is comparing with is smaller. Okay, 38 is larger, keeps going. 36 larger, keeps going. 15 is smaller, and that's the stopping condition of inner loop, and inserts it over here. Okay, but the outer loop is still going on because we still have 2 more elements, so it's going to come back to 50 and it's going to start again. All right, who wants to try this one? A little bit complicated. Again, same thing. The only complication is going back. That's the only thing. Goose, you want to try? Yeah, go ahead.
What's the deal with the swap?
You don't need swap over here, so you can forget about swap. Oh, remember in selection sort, there were 2 numbers and it was switching like this.
Yeah.
So basically, you are saying that the number index over here has to go over here, and this number over here has to go over here. That's what swap does.
So you got 4 I equals 0.
Okay.
Array dot line.
Excellent. Wow.
Your iterator,
Okay.
and then a second loop inside of this. And it'd be for j equals I minus 1.
Yeah. Okay.
And I don't know, is there some sort of difference here?
Yeah. So in the top one you have, what is it? Less than. Right.
Yeah.
So if you are going backward, it's going to be greater than. Remember the difference. If you're going forward, then you have the condition where I is less than length, whatever. If you're going backwards, the condition is going to be so. So instead of less than, it's going to be greater than.
Oh, okay.
So j is greater than.
Yeah, j is greater than array dot blank. Okay, got it.
No, not array dot. So we are going backward. So the condition would be 0, right? So it keeps going back until it reaches. So the forward loop is until you reach the end of the array, which is the length, right? Backward loop is until you reach 0 or negative 1 or whatever you want to say.
So J is greater than
Negative 1, yes. So it will stop at condition number 0.
Okay. And then J. Exactly.
Yes. Excellent. J minus minus.
And then,
Okay.
and then insert if. Do I get like an insert or do I have to like?
You don't need an insert.
No, I have to
You don't need
figure
a-
that out too.
No, you don't need an insert over here.
Okay, so it's insert if I is
So
If I is.
it's
less.
oops. So let's start with this one. So you have 19, right? Your inner loop is comparing this with this, right? If it is greater, what does it do? How do you translate this into the code?
So if I.
Oh, forget about this. I'm saying if the visualization. I'll keep it over here if it makes sense to you.
J.
Huh? Yeah, you already have the loop running. Yes. First comes the condition. What was the condition?
If I is less than J.
Yeah, okay. Go ahead and write it out and see if I is.
Less than J.
Okay. So we are comparing the elements. So just use the word array and then I,
Oh yeah.
right? So that would help.
R. Like that.
Yeah, yeah. So R, I is less than J. Is that the right condition? What do you guys think? So this is my current one, 19. This is RJ or RI. Which one is this?
I. The
Okay.
19, right?
Yeah, 19 is I. So my J is this one.
47.
Okay, yeah, excellent. So if it is, what is the condition again? Is less than.
Yeah.
Okay. So this means if it is less than, what do I need to do?
Move past it.
Yes. How do you move? What is going on over here? What do you think is happening? So
Is it another loop or something?
no,
Just-
no loop, just an assignment.
Okay.
So you this index.
So we're just
Is
doing
plus-
swaps
is-
every time.
Again, there's no. We are not swapping. We are just moving this value to the next index.
Right.
No, there's no swapping required right now. Just an assignment. So how do I assign?
J to I or
Yeah.
something.
But the next one plus one. So this if this is J,
Mm-hmm.
what is this index? J plus one.
J plus 1.
Yeah. So I'm going to move my J ahead. So I'm going to say my array J plus 1 is equal to array J. Array J plus 1 within the index, okay, is equal to array J. Okay. So whatever the value is over here is going to go ahead and sit over here with that statement. What happens to this value? This value kind of disappears, but you won't worry about that. Right? Okay. So what happened? It came over here now. You did the comparison again. Is true, so it swaps it over here. Keeps going, keeps going, keeps going. Now this condition. So you have reached a condition where that is false.
Mm-hmm.
What happens in this case?
You insert I into J plus 1.
Right. So first of all, my inner loop, I need to stop my inner loop.
Uh-huh.
I don't need to process this anymore, right? My inner J loop. So how do I stop this? We saw this in bubble or selection. What statement did we use to stop the loop?
Return? I don't know.
No, I don't want to exit the. If you do a return, it's going to exit the whole
Stop
function.
everything.
Yeah, I just need to exit the loop.
I guess I wasn't paying that close.
Anybody else? Break.
Break.
Yeah, go ahead and. So if. Oh no. So you already have a if.
Uh-huh.
When you're going to break, else.
Yes.
If that is false, so you already have your if. Yeah, go ahead and put in else. Else, go ahead and break. So if this condition is false, it's going to break the inner loop and come outside if. Okay. Now what you have to do, you have to assign, you have to stop the condition. So your inner loop is done. If you close, you can close your inner loop,
Okay.
and everything else would be outside the inner loop now. Inside the bigger, the outer one. Okay? Now what do you have to do? You have stopped it. You came over here, you just need to assign this one to this open position. How would you do that? What is this open position? We did it in our if statement.
J plus 1.
J plus 1, okay?
But am I going to be able to access that value now
Um,
that we're not in that loop anymore?
Yeah, if you break it,
Aren't you outside of that loop?
do you have access to that J or not?
No.
Okay? If you want
No.
access, what will you do? Huh?
Okay.
Either you can use a var keyword and do the hacky way, or declare J on the top as a global variable. And the reason is we need access to J.
Okay.
Okay? So let's suppose you already have access to J.
Okay.
Okay? So go ahead, and what will happen now? So J plus 1, you were right. Now my J plus 1 is going to be assigned this current value. How would I do that? R.
J plus 1
Okay.
equals
Equals to,
R I.
yeah, whatever that value is. Yeah. Ideally, we would save that item I on the top in a value,
Okay.
so that it remains
Just
the
like-
same. Yeah.
just
So
like
for
the-
example, yeah, you can say val is equal to R I, so that your I changes, but you will still have this val, and this way you would just say assign this val to this open position over here. Okay, and this will go ahead and insert it over here, and then we'll be back to your outer loop. Okay? All right, excellent job. Thank you. Okay. Now I understand it's not easy to come over here and kind of do it. But that's how you just need to show the willingness to the interview. I'm telling you, you are going to get help. But if you go up and you're like, oh, I have no idea, and just stand over there, it's not going to work. Okay. Again, recommendation: please talk it out. Whatever you're thinking, wherever you are stuck, talk to the interviewer. Make sure that you are having that conversation. Okay. Don't just like stand over there and be like, oh, I'm thinking. Right? I have done that, and I failed those interviews badly. And then I went back, watched some YouTube videos, looked at how people do interviews. That was what they were saying is, the thing is, the interviewer has no idea whether you absolutely don't know or you are just thinking, right? We interview a lot of people, and there are generally people who have no idea what it is, and they're just standing over there. So you want to differentiate yourself from them. You know it. You're just trying to think, okay, how do I come up with this algorithm? So just think aloud. Yeah, okay, I'm trying to think. Maybe I need a for loop, two for loop. The first one is going to go from here to here, and inside I'm going to do this. Write something. If you get stuck, your interviewer will help you. Okay? You want to try again? All right, so this is insertion sort. What is the time complexity? 2 for loops, n squared. Okay, worst condition is n squared. Right? Insertion sort, n squared. Best case is a little bit better, but usually it's still inefficient algorithm. Okay? One thing I want you to note is the space complexity, right? Remember I said there are two components, time complexity and space complexity. Usually when people ask the question about complexity, the first time they're asking basically what is the time complexity, okay? But still there might be case if you are good with time complexity and you answer quickly and you are correct, the next question usually is what do you think is the space complexity, okay? Just to give you an overview, all these algorithms that we have looked, till now, bubble, insertion, selection, and was there one more? No, these three, right? Did we look at three? Bubble, selection, insertion, okay? All of these, 0, 1 basically means it is not going to take any extra space. That's what it means. Okay, and you can see why, because I'm passing you an array and you are not declaring a new array. If at some point you are having a new array and you are assigning this value to this one and doing some calculations trying to sort this means you are using up some space. All right. 0 1 basically means that whatever array, whatever space you are getting, you are just using that space and solving this algorithm. Okay, so the algorithms that we have looked are all O1. Basically, they are not using any extra space. Okay. Now I want you to look at this one, quick sort. Okay. I would ask anyone to come and solve this. It's a little bit more difficult. It uses recursion, and it's not that it's not possible to write it out. You can, but you will still need a little bit more practice. Okay, I would recommend go back and solve bubble selection and insertion first, and then see if you can write the quick sort algorithm. But what I'm going to do is I'm going to go through this, and I'm going to explain how this works. Okay, now just give me 15 minutes and we'll end the class at 8, but this is difficult, right? It's not easy to understand quicksort. Okay, we'll talk about quicksort, and quicksort is used in most of the algorithms when you're using sorted. Okay, so quicksort is part of algorithms that are called command and conquer. Divide and conquer. So what it does is it divides the array and then sorts portions of that array. It makes small, like this array over here. It's going to break this array into smaller parts, and then it's going to sort them. Okay, that's there are a few more algorithms that do the same thing, and they are more efficient. But those are called divide and conquer algorithms. Okay, so quicksort is one of the basic, more easier and a little bit more basic ones. But the concept is that it is going to divide the array into smaller parts and then sort those smaller parts, and the result eventually is going to be that the whole array is sorted. Okay, so it's a divide and conquer algorithm. All right. Now, how does it do it? It uses a concept of called pivot, P-I-V-O-T, pivot. Okay. What is a pivot? It's the same English term that we use, like a pivot, right? What it does is it selects a pivot, one of the numbers over here, and then says that all the numbers that are left to it are going to be smaller than the pivot. All the numbers that are right to the pivot are going to be greater than that number. Okay, remember the binary search? It picks a number and less than and greater than. The same thing over here, but it's called pivot. So it's going to pick a number from the array and it's going to call pivot. And I'll talk about that. How does it pick that pivot? It doesn't matter right now. What is important is it's going to pick a number from here and it's going to call it pivot. Okay, that would be the starting point. So all the numbers eventually, it says that all the numbers to the left are going to be less than the pivot, and all the numbers to the right are going to be greater than the pivot. Okay, is that clear? All right. Now, what is going to be the pivot? There are three options. The first option is that what we are going to be looking at is you always pick the first number, the first index, and say that that is going to be my pivot. Okay? There are no changes to the algorithm, whatever pivot you choose. Right? But there are three options. The first is you pick the first number and say this is going to be my pivot. The pivot is going to change over time. Right? The second option is you pick the last one as the pivot. Okay? The third option is you pick any random number and call it pivot. Okay? Again, the point over here, it does not matter what the pivot is. The only condition is when you pick a pivot, you're going to run the sorting algorithm. Eventually, everything to the left is going to be less, and everything towards the right of that pivot is going to be greater. That's the more important concept. But again, when it comes to pivot, there are three options. You can pick the first one, the last one, or any random number over here. Okay? All right, we'll understand the algorithm with the first index. We'll pick this one as a pivot always, and we will see how that works. Okay? But when it comes to the writing of the algorithm, it doesn't matter what the pivot is, because you will see eventually the pivot is going to change. Yes, Chris?
So the less and the greater than the pivot is when it's done.
Mhm.
Or it's saying that we pick the pivot and we just assume that
No.
everything.
We pick the pivot, and then it's the job of the algorithm to, whatever the numbers are over here, put them in, or should be less than, and whatever the numbers are over here are going to be greater than.
So eventually your pivot point is the last element and it's the greatest number in there?
Eventually, yes. Yes. For example, if I start right now at 3, if my 3 is, right? So I want all the numbers that are greater than 3 on this side, and all the numbers that are smaller than 3 on this side. Right now, that's not the case, but that's the condition. It's going to say, are the numbers towards the right greater than? No, I see some smaller, so this means I need to run this algorithm. Okay, so it's going to go ahead, divide it, and make sure eventually all the numbers in every iteration are going to follow that concept. Okay, it doesn't matter what pivot you choose. You can start with 36, and you have to make sure that all these numbers are greater than, all these numbers are less than. Okay, and that's the algorithm. We will take a look at it.
So you don't know the location that the pivot is going to be.
It doesn't matter. Yes.
You just know that everything before it will be less.
Yes, that's the important part. The position of the pivot, the starting condition does not matter. Why? Because the pivot is going to change. You will see when the algorithm runs, it's going to change the pivot. We just need a starting pivot.
The index of the pivot changes. You don't change what the value of the pivot is.
No, we are going to move the value also. Yeah, this condition based on the value. The index doesn't matter over here, right?
Right.
The value should be greater than less than. Yeah, index doesn't really matter. Because we're trying to sort the numbers, the elements that are inside the array, not the index. You see what I mean? So, for example, my pivot is 3. So all the numbers over here should be greater than 3. All the numbers should be less than 3 on my left side. Eventually, it matters. Right now, it doesn't matter. It's only for the pivot. For example, my pivot, all should be great. It doesn't matter if 44 comes first, 38 comes first. Does not matter.
Okay, so
These are going to be eventually all sorted out.
I can create like 2 arrays, and if it's
No,
greater,
no 2
I
arrays.
push it there. If it's less, I will push it there, and then I will join them.
Right. But that's not quicksort. So if you are creating 2 arrays, you are taking up space.
Okay.
Right. So the time complexity, the space complexity goes up.
Right.
Okay. So you see over here. Okay. So it's not efficient, but still it's a better complexity. So we will see how it works. All right. All right. So let's go ahead and start this and see how this is going to work, and then we'll come back and see. Pause. Let me start in the middle so that you guys can actually see. Because the initial one, you won't be able to differentiate because it's only one number. And then I will come back to this one. Oops, it's too fast. I need to pause, and then I want to go back. Okay, what am I doing wrong? Pause. Still, okay, I need to refresh this. All right. Okay. All right. We are looking at quicksort. Let's make it slow. Sort, go, and pause. 44, 38. Okay. Let's skip ahead and see. I want you guys to see in the middle, and then you can start. Okay, let's start from over here. We'll come back and I'll go through the initial ones. It's kind of a little bit difficult to see the initial ones. So I'll complete the algorithm and then come back to the initial. Okay, let's suppose that my pivot is 38. Okay, so all the numbers towards the right of this number 38 should be greater than, and all the number less than 38 should be on the left side. Okay, right now we can see that 5, 15, what else? 36, 26, 27, 4, 19 are on the wrong side. Okay, they should be before 38. Okay, so that's our pivot. Let's see what pivot does. It starts with the next one and says it is less than 38. Okay, it doesn't swap right now. It has noted that there's a number next to me that is less than 38, and it's going to stop over here. It doesn't do anything, right? It has made a note of it. Okay, my pivot is still 38. The comparison is still with 38. Okay, now it checks 47. 47 is greater than 38. All right, still makes a note of it. What this is doing is it's creating a boundary. Okay, so any number that is less than 38 should be on this side, should be right next to 5, right? Anything that is greater than 38 should be after this boundary 47. Okay, what do I mean by this? Let's see what happens. So it checks 15. 15 is less than 38. It moves it over here. Again, what is happening? 47 is the boundary of all the numbers that are greater than 38. Okay, any number that is less than 38 are going to be on this side. Okay, it's not swapping 38 right now. It's making it's kind of breaking down this array. Okay, so for example, it goes to 36. 36 is less than 38, right? So it should be before 47, whatever this boundary is. It doesn't matter what the number is, but this should be before this number. So it's going to swap these two. Now goes to 26, less than 38. It has to be on this side. So it is going to swap 47 and move it over here. Okay. Looks at 27, still less than 38. It's going to swap this too. Okay. So this is the boundary for all the numbers that are going to be greater than 38, and all the numbers less than would be somewhere over here. Okay, 44, what happens? Is greater than 38. Does it need to change position? It does not. It's already in the correct position. All the numbers that are greater than 38 should be pushed towards the end. It's already over here. It's already inside this boundary over here, so it doesn't need to change anything. It's going to skip that. 46, same thing. Greater than 38 stays over there. 4 is less than 38. What is it going to swap with? 47. Okay? So it's going to swap these two numbers, and it's in the right position. Goes to 19. Again, smaller than 38 should be swapped with whatever the boundary of the largest number is, which is 44 right now. So we're going to swap these two. 50, greater than 38 stays the same. 48, greater than 38 stays the same. Okay? When this is done, what it does is it is going to swap itself with whatever the boundary is. Okay? Whatever the smallest number at that boundary is. So it's going to swap it with 19. Now, are all the numbers smaller than 38 on the left side? Right? And all the numbers that are greater than 38 are on the right side. So my 38 is my pivot. I have confirmed this condition that all the numbers that are smaller than 38 should be on the left side, which is my pivot. So this is confirmed and this is confirmed. Okay? So this is what it looks like. Right, my pivot is 38. All the numbers towards the right are greater. All the numbers towards the left are smaller. Okay? Now this is where the divide and conquer comes in. Alright? Now it's going to take this portion of the array and it's going to sort that array with the same algorithm. Right? It's recursive. It's going to go ahead and apply the same rules to this part And in this case, my smaller array over here, my pivot is going to be 19. Because we are saying our pivot is going to be the starting number. Okay? So what happens over here? Starts with, so now it is going to divide and it's going to sort this array, and then later it's going to sort this array. It's dividing the array into smaller and smaller portions until there's only one single element left. This means it's sorted. Okay, let's see what this means. So starts with 19. Okay, this is my 19 is my pivot. So all the numbers greater than 19 should be on the right side. All the numbers less than 19 should be on the left side. Same rules. Checks with 5. It's in the right position. 15 still in the right position because it's less than. 36 is greater than 19. So this is my boundary of all the numbers that are going to be larger than 19. Okay? 26 larger than 19 stays over there. 27 larger than 19 stays over there. 4 is smaller than 19, so it needs to be swapped with 36, which is my boundary for the larger number. So it swaps these two. Okay? End of this small array. Everything is good. The last step is to swap itself with whatever the smaller number is, whatever this boundary is. Okay? Whatever this number is, whatever this boundary is, that pivot is going to sort itself, swap itself. Now all the numbers that are less than 19 are towards the left. All the numbers that are greater than 19 are towards the right. Okay, this condition is met. This is how it looks like. Now remember, this is a divide and conquer algorithm. It breaks down into smaller parts. Now it is going to break down this part of the array. It's breaking down smaller until there's only one element left. Right? Start with the whole array, divide it into two parts, and then it sorted this one. Right now it's going to divide this one and it's going to try to sort these three elements. Okay? So my pivot is going to be 4. All the elements to greater than 4 are going to be on the right side. All the smaller will be on the left side. In this case, 4 is already in the correct position. Comes over here. There's nothing to swap with. It's going to stay over here. Okay? Now, what is next is going to divide this one also into smaller part. Now it's going to sort 5 and 15. Okay? It's already in the correct position. Stays over here. 5 is in the correct position. Now it's going to divide the array again into a smaller part, but now only one element remains. This means this is the stopping condition. This means this small part of the array is already sorted. So it's going to exit out of this and then go on to the next one. It's going to start sorting this part now. Okay? Comes to the next part. Again, divide this into smaller parts. So 26 is my pivot. Everything towards the right greater, everything towards the left smaller. Greater in the right position, 36 still in the right position, nothing to change. This is sorted. Alright, sorts this. This is in correct position anyway, so it's going to come back over. Only one element remains. This is already sorted, don't have to do anything. Moves on to the remaining unsorted array. Okay, you can see it's within few conditions, it's already sorted. It's almost sorted. Okay, my pivot is 46. Same condition over there. 46 greater, fine. Less than 46. Okay, it's going to swap these two numbers. Right? This is my boundary. 50 greater than 46 remains the same. 48 greater than 46 remains the same. Okay? Swap 46 with 44. And this part of the array has been sorted. Okay? So it's going to break down this into more smaller arrays. Comes to the left of the array. Pivot only one, so it doesn't need to sort anything. Okay? Goes to 47. Same thing, greater than on the right, less than on the left. So 50 remains the same. 48 also should remain the same. Okay? So this means 47 is sorted. Last two starts with 50, ends, moves it, and that's it. Okay? Comes to the smaller array, but it sees that there's only one single element. So this means my array is sorted, and this should end over here. Okay. Now, I hope you guys see it. You don't have to solve it right now. But the smaller arrays, it's using the same algorithm again and again. So it's called recursion. It's calling itself again and again and again. This technique is called recursion. Okay? Why am I calling it recursion? Because it is breaking itself down into smaller arrays and it's sorting them using the same quick sort algorithm, same logic over here. For example, this one, right, when it breaks down into these two arrays, right? How is it going to, what is it using to sort this part of the array? It's using itself. It's using the same algorithm. Okay, so when you're using yourself again and again, it's called recursion. Okay, a little bit more advanced technique, but that's how quick sort works and kind of a little bit makes it more efficient and faster. Okay, you guys want me to go through it one more time? Whiteboard it? Oh, this is difficult. Yeah, I will take some time to whiteboard this thing.
It seems like you have to assign like a bunch of arrays and stuff. Well, not a bunch, but
Not a bunch. You can use the same one. Again, it's
Right.
recursion.
Same
You are
one.
overriding the same one.
Right.
Yes. Okay. The time complexity of this, if you look at the first one, n squared, is still in the worst condition is n squared. Same as your bubble sort, insertion sort, selection sort. Okay. Then why would I use quick sort if the worst is still same as bubble sort or insertion sort? Why would I use quick sort and why is quick sort used? Let me give you a assumption that quick sort is used a lot. Actually, a JavaScript sort function, they use quick sort. We'll come to that. But let's suppose quick sort is being used. It's considered efficient algorithm. Why do you think even the worst condition over here is still the same as bubble, insertion, and selection sort? Why would you still use quick sort? Because the average is good, right? Worst case means that every single data, every single element in your array is in unsorted order, and every single it has to sort. Okay, how true is that? Not a lot of time. Okay, if you have like a million data set, you know a lot of them might already be sorted, right? So quick sort is good if it is an average rate. It's a lot better than n squared. Okay, n log n. If you look at the graph for it, we have it's better than n squared, especially for a larger data set. Quicksort is better than n squared. Okay, not for a extremely large data set, but a medium-sized data set, quicksort is going to work good for you. Okay, because of the average case, that's why quicksort is used more than bubble, insertion, or selection sort. Okay. The next question. If you look at the later ones, you have radix sort, counting sort, bucket sort. They are better than any one of these, right? Why would I still not use them? They're used, but why do you think you would still not use them? Any thoughts?
there's so much if you have really big data sets.
It's going to matter. What again? Why would it matter? It's the space complexity. When it is this efficient, it is using some kind of a space as well, right? So when you have a larger data set, again, larger, I'm talking about millions and millions of rows. Okay, so you need to come to a compromise if you are using one of these, which are extremely efficient, but they are also using space, which is not O1. Okay, so you need extra space if you're using these algorithms. That's what the comparison comes in, and that's what makes a determination. Okay, I can use the most efficient algorithm, but I'm also sacrificing some space. So it depends on your conditions if this is okay or not. Okay, so in this case, JavaScript uses. Okay, that's a wrong statement saying JavaScript uses quicksort. Okay. The question is, this is my question. What do you think JavaScript uses? Which algorithm would JavaScript be using? Okay, don't say it now. I'll ask you. Somebody else. What algorithm is JavaScript using?
When you say the best one is quick sort.
Best one is quicksort. Okay. Anybody else?
Quick sort.
What is it, Raymond?
Yeah, the quick sort.
But what do you think is JavaScript using? Selection sort. Anybody else? Any other? You can pick any one of them. Just like bubble sort. Okay, bubble sort. Nobody's using bubble sort. That's for sure. Okay. Bubble insertion. Yeah, bubble is definitely. What do you think, Chris?
I don't know which ones, but I remember you saying it decides on one based on your data.
It decides on one. Okay, that's kind of close. Okay. So the answer is you don't know. You don't know what algorithm JavaScript is using, and the reason is, remember what is JavaScript? JavaScript is based on the browser that it is running on. Remember, Chrome uses a JavaScript engine called V8. Mozilla Firefox uses something called SpiderMonkey. Let's see. Safari uses JavaScript Core. Internet Explorer or Edge uses something called Chakra. Okay, all of these are different JavaScript engines. All right, all of them are using different sorting algorithms to run your code. So if you run the function called sort, which is available in JavaScript, if you run this sort in Chrome, it is using a mixture of quick sort and, depending on the data set, I think insertion sort or one of those. If it's a smaller data set, it uses, I think, one of these. If it's a little bit larger, it uses quick sort. Mozilla Firefox has a different implementation of the sort method. Okay, so you don't know what algorithm exactly you're using. You can look at the documentation for the browsers and figure it out. But every browser has a different implementation of the word sort. Again, remember JavaScript is just a specification, right? Remember ECMAScript, that's the organization. That is saying that if you want to render JavaScript, you need to have a method called sort. That's all they're saying. What do you do in this method behind the scenes? That's up to the browser. Chrome is saying I'm going to use quick sort, fine. Mozilla Firefox says I'm going to use bubble sort. Okay, go ahead and do it. It doesn't matter. Okay, so what happens is where your code runs on which browser, that determines what sorting algorithm it is using. Okay, remember JavaScript is actually written based on these engines. Remember Node.js? One of the guys took the JavaScript engine from Chrome and created Node.js, right? So JavaScript itself, behind the scene, this is written in C, C++. Okay, so all your functions, all your sorting algorithms, they are determined based on what browser you're running your JavaScript in. If it is Chrome, different sorting. If it is SpiderMonkey, which is Mozilla Firefox engine, it's a different one. Safari uses JavaScript Core, so that's a different sorting algorithm. Okay, there's a chance they are using the same one, but it does not matter to us. It means that the sorting algorithm will be depending on the browser that your JavaScript code is running. Okay, does it make sense? Okay, so there's a variation of what goes behind the scene. But all of these browsers are going to have a JavaScript function called sort. Okay, now behind the scene, they are doing whatever they want to do. Okay, and that's the whole of JavaScript. JavaScript, the ECMAScript, the organization only defines what you need to have in your engine. It doesn't define how it has to work. Okay, how it has to work is based on the browser. All right, any questions? Okay, all right, well, that's all I have for today. Please work the rest of the time, work on your projects until 9:30. We'll be here. All right, again, this is not a short class so that you can leave. It is short. I'm making it short so that you can work on your projects. All right, I hope everybody understands that. All right, I will see you guys on Thursday for the last lecture. That's going to be on data structures. So I have a quick question.